On page 197, we find problem 23. A 13-foot long ladder is leaning against a house when its base starts to slide away. So I have my 13-foot ladder in this diagram, and the base is sliding away, which means the top is sliding down. By the time the base is 12 feet away from the house, the base is moving at a rate of 5 feet per second. We're asked a few questions. How fast is the top of the ladder sliding down the wall then? At what rate is the area of the triangle formed by the ladder, wall, and ground changing? And at what rate is the angle theta between the ladder and the ground changing then? So we're asked 3 questions. We'll just handle them one by one. So to start off, how fast is the top of the ladder sliding down the wall then? All right, so just to summarize what I know, I have a 13-foot long ladder, and I'm given how far it is away from the house at a moment in time, right? Because it's sliding away, it's not always 12 feet away, but at that moment in time, and I'm given how fast that spot is sliding away from the house. The bottom of the ladder is 5 feet per second. So I've drawn a diagram, and I want to introduce some variables. And if you took a very good look at your author's picture, you'll see he's already done this. But we're going to call this distance x and this distance y, right? And that's a natural thing to do, but I think it's important to denote it. We're also going to assume that the wall and the ground make a right angle. Well, right away, I think you can probably figure out a relationship between x, y, and the length of the ladder that will help us in this problem. The base of the ladder is moving away from the house at a rate of 5 feet per second. So that's dx dt, that's the rate of change of that. And I would in fact say because x is increasing, I should call that positive. Okay, I'm asked for dy dt in part A, right? I'm asked for how fast the top of the ladder is sliding down the wall. And the only other thing I know is that I'm looking for this rate at the moment when x is equal to 12 feet, right? That's what the problem said, right? Is that all this information is happening at that moment when x is 12 feet. All right, so looking at my diagram, a relationship between x, y, and the 13 feet would come from the Pythagorean theorem. X squared plus y squared is 13 squared. This is the equation I need to take the derivative of with respect to time. X and y are both changing. They're functions on time. So I have to use the chain rule for both. The derivative of x of t would then be 2x times dx dt plus the derivative of y squared, 2y times dy dt. And then the derivative of 13 squared, well, that's a constant, so that derivative is going to be 0. All right, so now if I think about it, I'm given dx dt, I'm looking for dy dt. I have a value for x, I need a value for y. And that's going to come from my original equation. Because at any moment in time, x squared plus y squared equals 13 squared. Because at every moment in time, the ladder has the same length, x and y are always the lengths of the legs of a right triangle. So x squared, 144, plus y squared is equal to 13 squared is 169. Take away the 144, and I'll get 25. And I'll see that whoever wrote this problem was being very nice to us because that tells me y is 5 feet. And I have something pretty easy to plug into this equation. All right, so now let's just substitute in x, y, dx dt, and we'll find dy dt. So let's see, I have 2 times x, which would be 24, times dx dt is 5, plus 2 times y is 10 times dy dt is equal to 0. So now I need to solve this equation. 24 times 5 is 120. I need to take that away from both sides. dy dt, 10 times dy dt is minus 120. Divide by 10, and I will find out that dy dt is minus 12 feet per second. It does not take this ladder very long to fall down the house. It's a pretty big rate of change, minus 12 feet per second, but I've answered part A. The rate at which the ladder is falling down the wall is 12 feet per second. When I say it in words, because I've said falling down, I don't have to use the plus or minus symbol out front. The ladder's falling down the wall at a rate of 12 feet per second. Part B. At what rate is the area of the triangle formed by the ladder wall and ground changing then, at that same moment in time, where the base of the ladder is 12 feet away? All right, well, just to make things a little simpler for us, I'm going to redraw the diagram. This time, I still know that dx dt is 5 feet per second. And this time, I'm not looking for dy dt, I'm looking for dA dt, the rate of change of an area, at the same moment in time. So I know that's when x is 12, and based on my previous work, I know that y is 5 feet. All right, now I need to write down a formula for the area of a triangle. Well, the area of a triangle is 1/2 base times height. In this triangle, the base is x and the height is y. Area is 1/2 base times height. Let's take a derivative. I'm going to have to think about the product rule because I have x times y, and of course the chain rule. dA dt is equal to, and I'll have a first function times a second function. Just for convenience, I'll let the first function be 1/2 x. So the first times the derivative of the second plus the second times the derivative of the first. Write this a little more nicely, and I have 1/2 x dy dt plus 1/2 y dx dt. I have a value to plug in for x, I have a value to plug in for y, I have a value to plug in for dx dt, and I need to know dy dt, and I'm very fortunate that in our part A of this problem, we found dy dt at the same moment in time to be minus 12 feet per second. So I have something to plug in all of the right spots to find dA dt at this moment in time. So I have 1/2 times x times dy dt plus 1/2 y times dx dt. All right, so let's see. 12 times 12 is 144 times 1/2. So that first part would be minus 72 plus 25 over 2, or 12.5. All right, so 12.5 minus 72. And I find that area is changing at a rate of minus 59.5, and those would be square feet per second. To express that in words,